Good afternoon, everybody. Welcome to another fun afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. Hope you all had a nice weekend. I did. All right, couple important things. First of all, on Wednesday, probably the beginning of the lecture, I will teach you my method for eliminating test anxiety. It works real good. I'll talk more about that on Wednesday, but I will cut it out of the video. I don't want that floating around. Maybe someday I'll be able to sell it, but not today. So make sure you stop by. If you can't come by, come to my office hour. It takes about 10, 12 minutes to teach and practice, maybe even 15 at most, but it's really effective. All right, another thing, don't forget, if you haven't uploaded your signature sheet to D2L, please do that. I'd appreciate it. That's in the assignment area. Upload it as a PDF file because you got to sign it. And if you don't have a scanner, I have files there that show you how to use your cell phone to do that. And I guess if you don't have a printer, handwrite it out and send it up. Hopefully you have a printer. If not, we'll get by. All right. Now, on Wednesday also, I will go through the Chapter 2 practice problems. I would highly recommend that before I do it, you try it. So if you have any questions, you can ask. And also, public service announcement from Dr. White. Hopefully you have learned, hopefully, hint, the table with the alkane name and numbers and the alkyl groups. All right, before I start with today's exciting lecture, any questions?
I'm looking on the assignments for the signature sheet. It says it's closed June 21st, so I can't submit anything.
Uh-oh. I messed up. Hold on. Bad Dr. White. Everybody know what this means? I've had a couple students who are from outside the United States who didn't know. Shame on you. Shame on Dr. White. After today, Joe, I will correct that. My apologies.
Okay, thank you.
No, thank you for letting me know about my mistake, bad Dr. White. All right. And Joe, could I ask you, near the end of today's lecture, remind me again, but better yet.
Yeah, sure.
Hold on. I love Post-its. Ta-da! Fix and it goes right over here so I can see it. But still, it won't hurt if you remind me. All right. No other questions? And again, thank you for letting me know about that mistake. All right. As I said last Wednesday at the time, guess what time it is? It's new chapter time. And this new chapter is quite exciting. We'll talk about things you'll never thought you'd learn about in organic chemistry, but it is organic chemistry. Everybody see chapter 3 on your screen? Thumbs up, people. Thank you. This chapter deals with alkenes and alkynes. Now, what we're going to be doing from here on out are talking about functional groups. Functional groups are a combination of atoms found in different molecules that always react the same way and provide similar properties in different molecules. Now, alkanes are not really quote unquote a functional group, but we treat them as such, but they're not really. But now we're going to get in some good stuff. This is when it gets fun. All right. Now, what's an alkane? Alkane is a hydrocarbon. I hope you all remember hydrocarbon, molecule with only carbon and hydrogens that contains a carbon-carbon double bond. Now, in, let me just remind you something in case you forgot. And what are the types of covalent bonds? There are three types. And you should have learned this wherever you took general chemistry. Here, Chem 112. I know I've taught this there. We got a piece. And the three types of covalent bonds are single, double, triple. Single bond is one pair of electrons being shared, double bond, two pair, and triple bond, three pair. So if I'm going to talk about alkenes, that's a double bond with two pair of electrons. By the way, a pair means two. So that means a single bond is two electrons, double bond four, triple bond six, but we usually talk about it in terms of pairs. So an alkene is a hydrocarbon that contains a carbon-carbon double bond. We show that by two lines between a carbon, two carbons. That's a double bond. Now, I'll never ask on a test, but some entrance exams, if you have an alkene with 5 carbons, how many hydrogens? The formula is CnH2n, where N is the number of carbons. Again, I'll never ask anything dealing with this on my test or final. Now, an alkene is a hydrocarbon molecule with only carbon hydrogens that contains a double bond. We'll also talk about alkynes, Y-N-E ending, and that's a hydrocarbon. Oh, it only has carbon, hydrogen atoms that contains at least one carbon-carbon triple bond. And triple bond, three pair or three bonds between two carbons. And we show that by three lines between two carbons. Two lines, double bond, three lines, triple bond. For those of you who know baseball, when you make it to second base, what do we call that? A double. I wonder if organic chemistry stole that from baseball, or maybe vice versa. And if you make it to third base in baseball, what do we call that? Triple. So alkene, a double bond, alkyne, a triple bond. Now, this chapter and the following chapters for just about the rest of the semester, you should be asking the following question. Why am I learning this stuff? Well, the obvious answer is someone told you had to take Chem 170 or organic chemistry so you could get into a program or into school, get admitted like to nursing school. But really, why did they want you to learn organic chemistry? And that's a question you should always be asking, including me, and I'll be answering that. So let's think about, why should I learn about carbon-carbon double bonds? Good question. Well, let's find out. First of all, I'm going to ask a question of you. Have all of you at least seen, if not eaten, a carrot in your life? Or seen Bugs Bunny eat one? I think you all have. And what color is the carrot? Orange. Why is the carrot orange? Because there's a molecule that makes the carrot orange, and it's called beta-carotene. And that's a common name, not an IUPAC name. Now, everybody see the structure of beta-carotene on the screen? Every bend in a line, this is the line method for not only rings, but you can use it straight chain too, which I don't, but here in Wikipedia they do because it's easier to software to do it. And here's a double bond, here's a double bond, another one, oh, more, lots more. I think there are 11 double bonds in beta-carotene. How Mother Nature came up with this molecule, I have no idea. But this is the molecule in carrots that gives it its orange color. How does it do that? Double bonds and what we call conjugation, which I'll never ask what's conjugation on test, but it's alternating double, single, double, single, double, single, have ability to absorb light. Now, white light is made up of many colors. How many remember from high school Roy G. Biv? Red, green, blue. Yeah, I remember. I still remember it. But anyways, carrots absorb all the beta-carotene you see on your screen, absorbs all the light except the colors that make up orange. It doesn't, and those are reflected. Now, your body can break up beta-carotene to another molecule I'll show you later in the semester, and it has a common name, retinol. Retinol. What's in your eye? The retinas. And when your body breaks this down to retinol, that helps you see better. Oh no, guess what? Let me move this out of my, hold on one sec. How many have you ever heard carrots make you see better? Help your vision? Well, it's true. I don't know how much and how much it helps, but the beta-carotene is broken up, stuff you use your retina in your eyes, and that chemical is retinol. I guess it's true. That's why Bugs Bunny sees well, because he ate a lot of carrots. Have you all seen Bugs Bunny? I don't know if they still watch, you still watch, hopefully you have. By the way, if I ever pull a generation gap thing on you, let me know. I don't know what you're talking about, Dr. White. Now, while we're in the produce section of the supermarket, there's another chemical called lycopene. How many of you have ever seen a ripe tomato? Or had one? I like tomatoes, especially since I'm from Chicago, with celery salt on it. If you've ever had Chicago hot dogs, they have tomatoes with celery salt. By the time I was 10, even my parents, we always, even on our salads, put celery salt. But anyways, there's a molecule similar to beta-carotene called lycopene. And you see the molecule on your screen. And if you notice, it also has a lot of double bonds. And what this does in your body, I really don't know how helpful it is. But for some reason, Mother Nature put this in tomatoes, and it absorbs all the light except the color red. And that's why when you look at a tomato, they're red. But you never thought organic chemistry involved carrots and tomatoes. It does. All right. How many of you have ever seen on TV or gone to the supermarket and bought a product that says on there, a cleaning product, and it makes things smell lemony fresh? I have, and you can see it on. Well, what makes things smell like lemony fresh? Well, it turns out it's an alkene, a molecule with a double bond. And that molecule is pronounced as called limonene. And here, every bend in a line, every end in a line is a carbon. And here at the bottom, you see a double bond. And right in the ring, there's a double bond. And here's a methyl group, and this is called isopropanol, which I won't cover in this class. But anyways, limonene has 2 double bonds in it. And when you buy something that says Lemony Fresh in there, they put some of that in there to make it smell lemony fresh. And it's found in all citrus, or most, I think, if not all citrus fruits, which limes are one. And that's how they put that lemony line. By the way, those of you with family members behind you, say hello from Dr. White. But anyways, visitors are always, I should say, encouraged and allowed. No problem on my part. But anyways, limonene doesn't have that much to do with cleaning, but it makes you think. And Madison Garden, Madison Avenue, in other words, commercials have you brainwashed that, oh, that's going to clean well. No, it just makes it smell well. I'll talk about how things get clean later in the semester. Yep, that's organic chemistry too. So we have alkenes, carbon-carbon double bond, alkynes, carbon-carbon triple bond. Now, triple bond, I'll talk more about, but one of the unusual things that I'll talk about later where you find a carbon-carbon triple bond is in, are you ready for this? Birth control pills. And I'll talk about that at the end of the semester, near the end. But Mother Nature never, ever made a carbon-carbon triple bond. Double bonds, yes. Triple bonds, no. Triple bonds are something organic chemists came up with. Now, I'm going to turn the switch, click this slide off, but I just want to talk about unsaturated hydrocarbons. Remember, a hydrocarbon molecule, carbon and hydrogens, unsaturated, a hydrocarbon that contains either a double or triple bond. Now, it turns out hydrocarbons have less hydrogen atoms than alkanes. I'll show you this later today. And as I just mentioned, unsaturated hydrocarbons, molecules, carbon and hydrogen atoms only that contain one or more carbon-carbon double or triple bond. And you'll learn today that the addition of hydrogen gas will convert an alkene double bond to an alkyne, a triple bond, to an alkane, a single bond. And by adding hydrogen, and I'll teach you later, you also need a catalyst. These two can be converted to a double bond or triple bond to a single bond. Now, one of the things, let me remind you, Dr. White has the fastest mouse wheel finger, this side and the other side of the Mississippi. So if I move too quickly, you can always ask, can you come back to that slide? And the answer will always be yes. Now, just a reminder, all the slides you see, type things on a screen, are files available to you in D2L, in this case, in the lecture folder of content, and is secretly named Chapter 3, Alkenes and Alkynes. All right, I forgot to pull this slide, cross it off, hold on. All right, now, when it comes to the rest of the semester, or a good part of the semester, I'm going to introduce you to a new functional group. Hi, everybody. Say hello to double and triple bonds, alkenes and alkynes. Well, I did that. Then near the beginning, I'll show you where you find them in the real world, or sometimes during the lecture, during the chapter, I'll do that too. And then we'll do nomenclature. Remember, nomenclature is a fancy word for naming. And then we'll get into the fun part, reactions, how you make them and how you react them. So that's the fun part. but that's because I'm a synthetic organic chemist, never asked you on a test, but synthetic is a fancy word meaning to make. And my training has been in making molecules, also making molecules once I got in industry that do things like soften your clothes, hold things together, and kill microbes and bacteria. I've done all that. So let's get back to chapter 3, nomenclature. Now, how do you name a double bond? Now here, throughout the semester, you'll learn that you take the alkane name and change the ending. And that designates what functional group it is. And a double bond has the ene ending. And I'll come back. Don't worry about, I forgot to take this out, this stuff. Dying, trying, we're not going to get into. A triple bond has a YNE ending. And again, for 2 or more, this, I forgot to take this out, I apologize. Now, let's take a look at how you name a double bond, and then we'll come back later today and do triple bonds. Now, first of all, I better get a molecule on the screen. Let me remind you of the 15-second rule. Wait about 10, 15 seconds after I write something till you write it down, because I might change my name, which I just did. Change my name, change the structure. Anyways, I'll change the name of the structure too. All right, let's take a look at this. Now, remember, there's always 4 bonds to carbon. I better hold on. There's always 4 bonds to carbon. Oh, that's broken. I got 4 bonds, 4 bonds. That's your friend. There's always 4 bonds to carbon, and never more, never less, whenever you write a structure. So let's look at the structure I have here. Now, these carbons, no problem. You can count like this one, 2 bonds, 4 minus 2 is 2 hydrogens. Now, let's look at this carbon. How many bonds to it? 1, 2, 3. So 4 minus 3 is 1, and that's why there's 1 hydrogen there. Again, count the lines or bonds to carbon, subtract that from 4. That tells you how many hydrogens. So that's why 4 minus 3 bonds is why we need only 1 hydrogen. Now, if I look at this carbon, how many bonds to it? The answer is 1, 2. 4 minus 2 is 2, and that's why there are 2 hydrogens. Now, the question is, what's the IUPAC name? Remember, IUPAC is the acronym for the official name. I'll never ask on a test, but I like to say it. It means pure and applied, let's see, IUPAC International Union, Pure and Applied Chemistry. It's cool to say that. Well, anyways, what do? You find the longest chain with both carbons of the double bond. Find the longest chain with both carbons of double bond. 1, 2, 3, 4, 5. Now, in this case, I don't have any branching, but we'll get to that. And that, if you look at the table for alkanes, is pentane. But for an alkene, a double bond, you take the A and the ending of the alkane and you change it to ENE. ENE means double bond. Take the pentane, drop the ANE, which I've done, and now this becomes pentene. But the double bond can be anywhere along this chain. And you look at the first carbon of the double bond that's closest to end of a chain, and you give that number the location. Notice this carbon right here, carbon 1 is the first carbon double bond close to the end of the chain. It is. So this would be 1-pentene. Again, find the longest chain. In this case, there's only one with 5 carbons. Name it as an alkane, pentane. Drop the ane ending and replace it with ene ending, pentene. And then what number carbon of either carbon of the double bond is closest to the end? And you number it, always starting at the end of an alkene, and name it, give the number. And so this is 1-pentene. Now, let's look at this molecule. And again, the question would be 3 points. Give the IUPAC name. Now, one thing I neglected to tell you that I better tell you now. Listen carefully. This is your friend, 4 bonds to carbon. Now I'm going to teach you your other friend that will help you in Chem 170 in organic chemistry. When you look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention like that, because that's where the fun is, that's where all the action is, and realistically, that's where a functional group will be. So whenever, and I do this instinctively now, I've been doing it a few more weeks than you have, a few more months, a few more years, a few more decades. Oh, I shouldn't have said that. But anyways, in case you don't know what oi means, look it up, it's Yiddish. And if you don't know, the next step, instead of saying oh, we say oi, and sometimes we'll go like that. Where do you think I should have had a V8? And the next step up is oi they, and that's like, oh. But anyways, oi. Remember, look for what's different now in a molecule. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. And hopefully it will. Does mine every time. So let's go back and look at the example we're doing. And the question is, what's the IUPAC name for this? And if I look at that molecule, I scan it real quick, immediately, just like flashing red lights from a fire truck to tell you to move over, hopefully you do, a double bond. That got my attention immediately. The rest of the molecule is important, but that double bond and tells me, look at me, I am important, and it is. And now how do you name it? You find the longest chain with both carbons of the double bond. Remember, both carbons, 1, 2, 3, 4, 5. There's another chain, 1, 2, 3, 4. Hopefully you've been practicing this. Not, please do it by Wednesday. So I'll go through chapter 2 problem set. Well, hopefully all agree 5 is greater than 4. Well, how many carbons is 5-carbon alkane, pentane? But I have a double bond, and you drop the ane ending of the alkane name and convert it to ene. So that becomes pentene. Now, as soon as I say pentene, I'm sort of there, but what is the lead carbon of the double bond closest to the end? That's this one. So it's 1-pentene. And finally, am I done? No, there's something left over. Oh, it's your old friend, the methyl group. And notice that's on carbon 3. So that'd be 3-methyl-1-pentene. And since Dr. White likes to share the fun, also double bonds or any functional group always have priority, lower number than alkyl groups. If you have 2 ways to number it. And here's your turn. Give the IUPAC name for the following molecule. Now, since some of you might not have learned the alkane name yet, 1 through 10, 5 is pentane, 6 is hexane, 7 is heptane. And when you're done, give me a thumbs up. Thank you. For those who are done early, please be patient. All right, let's do it. Now, when I look at this molecule, what do I see that's different? A double bond. That gets my attention immediately. I know I'm dealing with an alkene, and the first thing I have to do is find the longest chain with both carbons of double bond. 1, 2, 3, 4, 5, 6. If I do this way, 6. So either way I count, the longest chain is 6. 6-carbon alkane is hexane, but a double bond, you take the ane ending of the alkane name, drop it, and replace it with ene ending. So hexene. Next, what carbon is the closest carbon of the two of the double bond to the end of the chain? And it's this one, which is 1. So this is 1-hexene. Now, as soon as I say 1-hexene, this is all spoken for. And what do we have left over? It's your old friend, the methyl group, or soon be old friend. So that would be methyl. And what carbon is it on? It's on carbon 5. Now, common mistakes students make are they'll call this 2, and then this is 3, 4, 5. They call it 2-methyl 5. And that's wrong, because the double bond carbon has priority, always gets a lower number. And that's how you do double bonds for now. Now, we're going to come back to this because I want to talk about something now that's very important. You say that about everything. Now, we're not going to deal with multiple bonds. So this I'm not going to. Well, actually, the way I have it written, multiple meaning double bond. So that the carbon, I've done this already, number 3. Find a carbon of the double bond that's close to the chain, give it a number, and indicate the position of the double bond or triple bond using the lower number carbon atom of that bond. We've done that. If more than 1, this is the one we won't do. And alkyl groups I just showed you are the same as we've done before. All right. Now, there are a couple IUPAC names. IUPAC names, and we'll see this throughout the semester, came only in about 1920. But organic chemistry has been going on for centuries. And we have what's called common names. And these are names that people to this day still use, and you'll find them even on ingredients labels. And there are a couple of common names that this is ethylene, and I won't ask you that on a test. Propylene, has this structure. I won't ask you that, but I will ask you to know acetylene, and that is a triple bond. And I can write it this way or this way. You can either left justify or right justify the hydrogen all the way on the left. My software likes to do left justified. Even when I tell it not to do it, it still likes to do it. So once in a while, I'll mix it. Now, acetylene, where do you find that? I didn't talk about where do you find triple bonds other than birth control pills. Let's talk about acetylene. How many of you have ever seen a movie or a TV program where they're going to cut out the lock of a safe? They bring in this torch that's real hot and they light it and they burn out the metal lock, punch it out and open the safe. Or if you've ever seen on TV where they show a chop shop, or if you've ever been in a repair shop where they're cutting metal, they have this very hot torch. And what is that? It's called an acetylene torch. Instead of burning methane, natural gas, or propane, stuff in the white tank for your barbecue, they burn oxygen and acetylene. Because of the energy of the triple bond, it's a much hotter, much hotter flame. That's why you can melt metal with that. And you can't do that with your gas from your stove. Otherwise, all your pots would melt. Ugh. Anyways, that's acetylene. Now, one I won't ask you, when you have a substituent, something here, and this is attached to it as a substituent, we call that a vinyl group. Vinyl. How many of you ever heard of vinyl floors? I wonder where the word vinyl came from right here. Now, how it became vinyl, I don't know. Someday I'll have to look on the internet, but it's a vinyl group. I will not ask that ever on a test. All right. Next couple of slides, I'm going to turn the switch, click. Will this be on the test to the off position, down like a light switch? Now, the double bond contains two types of bonds. And this you should know. One is called the pi bond, Greek letter pi, and the other is the sigma. This you should know. And I'll mention it later when we get into the chemistry. So a double bond has one pi bond and one sigma bond. Now, carbon-carbon single bonds are just sigma bonds. Now, they're not equal, they're different. And that difference is important and also very fun to use. Now, the pi bond is the Greek letter pi. Now, it has different hybridization orbitals, which I'm not going to ask you to remember, and has a bond angle of 120, and there's no rotation around a carbon-carbon double bond. Now, what does that mean? This is very important, but it won't be on a test. Here I have, say the black center is a carbon, and the line between it, or the cylinder between it, is a carbon-carbon single bond. And notice I can rotate this. And around carbon-carbon single bonds, there's rotation. Now, here I have a double bond. How can you tell double bond? Two lines, 1, 2. Unless I break this, which I'm not, because I couldn't find my others. It's the only one I have in my house now. So it's very valuable to me, because you can see it. There's no free rotation like a single bond. That turns out to be very important. Now, if we have a carbon atom, again, switches off here. A carbon atom that's going to be involved in a double bond, these gold-colored spheres are called orbitals. And orbitals are, if you had the power to stop all time and movement, that's the probability where you'd find electrons. Each sp2 has an electron. So if I were to stop the electron moving around, and no, they don't move around an atom like this planets of the solar system. No, they don't. This is where I'd find it. One in that one, one in that one, one in that one. Now, carbon atoms involved in double and triple bonds also have what's called a p orbital. And this blue, if I were to stop all motion, well, I'd be powerful. In that area is where you'd find an electron. And by the way, the bond angles between the sp2 is 120 degrees, which I'll talk about later. Now, when you bring two carbon atoms together to form a double bond, you have overlap of the sp2 orbital here, one electron here, and it forms a sigma bond. Again, switches off on this slide. And then the p orbitals, one here, one electron here, an electron, this one, overlap, share, and that's called the pi bond. Now, in the blue, you have two electrons somewhere in that area floating around, and they hold together the two carbons along with the sigma bond, two areas in this gold area. And because of that, think of like having your finger like this with rubber bands, and you can't move it. It's locked in place. And that locked in place has a very important aspect of double bond, because double bonds, unlike a single bond, the carbons are trigonal planar. They're flat in that plane, the gray, and notice the bond angle is called trigonal, like a triangle between two hydrogens and a carbon. You could have a triangle. Let's go back and do another nomenclature, double bonds. Now, did I tell you that IUPAC has done such a great job that two different molecules never, ever have the same name? If you have two separate molecules, they never, ever in IUPAC have the same name because they've done such a great job. So let's look at two molecules to have fun with, naming them. Now, because of the geometry, I didn't show it earlier, and the fact that a double bond is fixed, I can draw a molecule like this, and for the time being, let's call this A, one from column A, and let's do a B. And here I'm showing the bond angles 120 degrees. Now, if we look at A, how many carbons in the longest chain? 1, 2, 3, 4. If you count the other way, you get 4. And for double bond, that would be butane. Drop the A and E ending, put ENE, butane. And what carbon is the lead carbon closest to the end of the chain? 2, if I started the other way, 1, 2, and this is 2-butane. Did I tell you, I think I did, how great a job IUPAC did? Never, ever do you have 2 molecules that have the same name that are different. Now let's look at B. I'm going to ask you how many carbons are in the longest chain. And hopefully let's count. You got it right. 1, 2. No, this carbon is bonded to that carbon. This is bonded to that carbon, linked like a chain. 3 as linked to that carbon. 4. 4 oh, that's butane. But it's a double bond. So that's butane. And what's the lead carbon of double bond? 2. Uh-oh, we got a problem here. A and B are different molecules. They're not the same because you can't have rotation around a double bond. But they have the same name. That can't be. Relax. Guess what? IUPAC knew about this and they have rules for this. And what are those rules? Those are cis-trans isomerism and alkenes. Double bonds due to no rotation around carbon-carbon double bond. We have what's called cis, same side of 2 groups or atoms on the same side of a plane of a double bond, and trans, opposite sides for 2 carbons or groups on a carbon-carbon double bond. So let's go back and look at our example. But first, I'll help you out. Oh, I should warn you, I was always the first one down in a spelling bee. Thank God for spell check on Word. And if I make a mistake spelling, correct me. Chemical names, I don't, but I think I spelled opposite right. Once in a while, I'll blow it. All right, now, if I had a plane like this, coming out like this, or pencil there, notice the hydrogens are on the same side or the methyl groups are. And that would be cis. And this actual name would be cis-2-butene. Now, if I look at B, the same plane, I have the hydrogens on opposite sides of that line or plane. Same thing with the methyl groups or CH3s because they're part. And opposite we call trans. So this has the name trans-2-butene. So A is cis-2-butene, trans, B is trans-2-butene. And IUPAC, it hasn't failed me yet. No 2 molecules that are different have the same name. How many of you ever heard of cis and trans fats? You know, medical science, which I believe tells us trans fats are bad for you and cis fats are better for you health-wise. And later in the semester, when we talk about fats and oils, there's a double bond in fats and oils that can be either trans, hydrogens on the opposite side, or cis, hydrogens on the same side, like in cis and trans-2-butene, and one is healthier for you than the other. Why? I have no idea. I'm a chemist, not a medical doctor. And with that, if I look at the clock, oh no, time flies when you're having fun with alkenes and alkynes. It's time for a break. I'll see you at 1:55. I'm going to get up and stretch. I'll see you in 5. Time to go again. Welcome back, everybody. All right, let's get back to nomenclature double bonds. Now, when you have two of the same group or atoms on one of each atom of the carbon of double bond, and they're on the same side of a plane, or think of it as a line going through the double bond like that, we call that cis. Same side, cis. When you have two atoms or groups on opposite sides of that same line, which is really an orthogonal plane, but it's easier for you, we call that trans. Now, the rest of the nomenclature is same, but this would be cis-butene, 2-butene. This is trans. And if we go back and look at these, Dr. White, how did you show stereochemistry or have cis or trans? When you have two of the same atom or group on one carbon of double bond, like I have here, hydrogens are here, you can't have cis-trans isomerism. Isomerism is isomers, molecules with the same number of atoms and types of atoms, but arranged differently in space, which this clearly is. So let's look at another example. And here it's important to show stereochemistry. All right, let's look at this molecule. Now, the first thing you should be doing is look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention like that this did. All right, everybody see the double bond right here. So immediately I know I have an alkene. How many carbons in the longest chain? 1, 2, 3, 4, 5, 6, 7, 8. That's one chain. Oh, there's another one. We could have 5 and come down here, 6, 7. And when you count chains, both carbons of the double bond have to be in that chain. There's another chain, but it doesn't contain both carbons double bond, so I don't have to count it. And hopefully you all agree 8 is longer than 7 or larger. So now 8 alkane is octane, but I have a double bond that's ane ending to ene ending. And now that's octene. Now, what's the closest carbon of the double bond to the end of the chain? The way I have it numbered would be 2. If I go the other way, it'd be 1, 2, 3, 4, 5, 6. Which is smaller, 2 or 6? Hopefully all agree 2 octene. Now, notice on this carbon, there's a hydrogen. On this carbon, there's a hydrogen. I'm going to let you try and figure out, are they an opposite or the same side as a line that would be right there? And the answer is same side. And same side, oh, look, someone was nice enough to write it on the screen there, means cis. So we have cis 2 octane. And as soon as I say that, all that's spoken for. Oh, wait, we got some left over here. And 2 carbons is an ethyl group. And what carbon is it on? Carbon 5. So it's 5-ethyl cis 2 octene. And that's how you do it. And here's a molecule for you to answer the question, what's the IUPAC name for this molecule? 3 points each. First, you got to find what's the longest chain. And then do the rest. And don't forget, when you're done, give me a thumbs up. For those who finish early, please be patient. I try and give everybody time to finish. And even when we're face to face, I do the same thing. All right, is everybody done? Let's take a look at this. Now, when you look at a molecule, you look for what's different. What's not a carbon-carbon single bond, what's not carbon or hydrogen atoms. Oh, look, a double bond. And therefore, we have an alkene. And the first thing I'm going to do is find the longest chain with both carbons a double bond. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's another chain too. 6, which is this carbon, then 7, 8, or 7, 8, doesn't matter which side you go to. Now, I hope you all agree 9 is greater than 8. Therefore, the longest chain, 9 carbons, nonane. But I have a double bond, and you drop the A and E of nonane and replace it with ENE, nonene. Now, what carbon of the double bond is closest to the end of the chain? And hopefully I'll pick 3. So that's 3 nonene. Now, you have cis-trans isomerism. If there were a line here, or plane, notice the hydrogens, I have a hydrogen on each carbon. Are they on the same side or opposite side of that line? And the answer is opposite. And someone was nice enough to write on there, the screen, opposite is trans. So we have trans 3 nonene. As soon as we say that, all that's spoken for, oh, look, we have something left over. 3 carbon alkyl group, which the center carbon is bonded to my chain, is isopropyl. And it's on carbon 6. So this is 6 isopropyl trans 3 nonene. Remember, cis is same side, trans is opposite side for a double bond. Now, the following you do not have to write down, but everybody know what that is? Transparent. You can all groan and boo at me. That's permitted. It's one of the clean chemistry jokes I can say in this class. Transparent, trans opposite side. All right, now let's go back, continue with double bond nomenclature. Now, what I don't have here, which I should, let's talk about double bonds in a ring. All right, everybody see on the screen, I have a 6-membered ring. Remember, we don't show carbons or hydrogens in a ring, the line method. Each bend in a line or each line is a carbon atom. So there's 1, 2, 3, 4, 5, 6. Now, we have a double bond, 2 lines between these 2 carbons. Now, same thing, name it as an alkane. Now here, that would be cyclo, because it's a ring, hexane. But again, drop the A-N-E ending at the and change it to E-N-E ending. So it's cyclohexene. Now, for the rings I've ever encountered, I think decades ago, and I'm not even sure I did, somebody once made a huge ring with a trans double bond. But for all intents and purposes, all the double bonds in a ring Mother Nature has done, and like 99.9999% chemists have done, organic chemists, it's always cis. So since everybody knows that, we don't put down cis or trans for a double bond in a small ring, like 6 or 5. I think 4 you can, but I'm not sure. 2, 3 you really can't. And larger, it's not really, you're going to see in organic chemistry that often. So the other thing is, when you have a double bond in a ring, one of the carbons is always going to be 1, the other 2. So one of these has to be 1, the other 2. And because of that, when there are no other functional groups, which is how we'll do it this semester, I'm done. Because since everybody knows 1 is 1, the other 2, you don't have to put a number. So that would be cyclohexene is the name of that. Now, what do you do when there's a substituent? Now, here we have a ring with a double bond. And how many carbons? I'm going to let you figure out how many carbons first. I'll give you 4.2 seconds. Go. How many carbons in the ring? Bonus time. Time's up. And the answer is 5. 1, 2, 3, 4, 5. It's a ring, so it's cyclo. It's a 5-carbon ring. I can cyclopentane, but it's got a double bond, and the ending becomes E-N-E ending, cyclopentene. Now, one of the carbons is going to be 1, the other 2, so I don't need a number. But oh, look, it's your old friend, the methyl group. And you number it in such a way that one of the carbons double bond is 1, the other is 2, and the alkyl groups get the lowest number. And notice the way I have it numbered, it would be on 3. So that would be 3-methyl cyclopentane. Now, cyclopentene, excuse me. Let's do this. If we said this is 1, that's 2, that's 3, 4, then this would be on 5. Which number is lower, 3 or 5? And the answer is 3. Now, common mistakes students make with a ring. They say, I'm going to make this 1 because I can make one of the carbons of the double bond 1, and I'll make this 2. Well, in that case, this has to be 3, 4, and this carbon is 5. That can't happen because one of the carbons of double bond has to be 1 and the other has to be 2. So everybody clear on that? All right. Well, I better share the fun, let you have some fun. And the question is, what's the IUPAC name for the following molecule? 3 points each. 4 carbon, in case you haven't learned, is tert-butyl. Now, this part of the semester is slow because we're going through a lot of nomenclature, but later today and coming weeks, it'll go faster because nomenclature will spend less time on and more on the fun part, reactions. And when you're done, give me a thumbs up. All right, looks like everybody done. I'll give you another 8.6 seconds. All right, let's do it. Now I have a ring. Remember, look for what's different. Ooh, a double bond ring. How many carbons? 1, 2, 3, 4, 5, 6. Hexane, it's a ring. Cyclohexane. It's a double bond. A on the ending is dropped and it becomes E on the ending. So it's cyclohexene. I had too big of a space there. Didn't want to confuse you. Now, one of the carbons has to be 1, the other 2. So if I make this 1, this 2, notice my alkyl group is on carbon 4. Now, I have a bad habit when I print, some of my letters look capital. If you were keyboarding this, they're all the same case, but if you mix them, I don't care. So that'd be 4-tert-butyl or T-butyl cyclohexene, and that's how you do a ring. Now, there are 2 skills that you should have when it comes to nomenclature. One is, here's the structure, give the IUPAC name. The other is, and that would be draw the structure for trans 2-hexene. Now, how do you do that? How do you decode it to know what to do? Organic chemistry is always the same, the names. Start at the right and move left. And as soon as you see an E on the ending, that means, everybody know 3 lines means exactly equal to or means, I better not, that's not a good, means a double bond. So if that were A and E, hexane, 6 carbons. Notice the double bond is at carbon 2. 1, 2, 3. Now it's trans, so that means hydrogens are on the opposite side. I have 3, I have 4, I have 5, I have 6. And remember, there are 4 bonds to carbon, so I know how many hydrogens to put in. And that's how you do it. Again, start from the right, move left. Look at the ending. ENE ending tells you double bond. What's the lead carbon? Carbon 2, and the hydrogens are trans. And here's one for you to try. Am I nice or am I nice? I got to share that you have some fun too. Draw the structure for cis-3 octane. And when you're done, don't forget to give me a thumbs up, or should I use the polling? You're such a small group. And now you're saying why last week I said, learn that alkane table and the alkyl group table. Because if you don't know that, you can't do this. All right, let's do this. How do you decode this to know what to draw? Start from the right, move left. ENE ending, double bond. If it were ANE, octane, 8 carbons. What's the lead carbon of double bond? Carbon 3. And cis. So I have 1, 2, show my bond angle, double bond. Cis means same side, so my hydrogens will be on the same for this class. So I'm going to keep it to hydrogens. That's 4, 5, 6, 7, 8. There's 4 bonds to carbon. And I'm putting in my hydrogens. Oh, let's do 2 more. These are fun. And don't forget, there's no such thing as a dumb question in my class. If you have questions, ask. That's why we're here to learn. You're here, and I'm here to help you. And why don't you try this one? Draw the structure for 5-methyl trans 2-heptene. You can't see it, so I'll write it on here. Cis is same side. Trans is opposite side. It warms my heart to see everybody working on their nomenclature. Thank you. I use that hokey line in the class too, but it's true. And notice organic chemistry isn't as painful as people say it is. At least I hope not for you. And when you're done, give me a thumbs up. All right, I think everybody's done. Let's do this one. How do you know what to draw? And you start from the right and move left. E-N-E ending. That means double bond. So if that were A-N-E, heptane, it would be 7 carbons. Whereas double bonds start, carbon 2, and it's trans, 1, 2. Trans means the hydrogens are opposite. Could have other things, but for this class, I'll keep it to hydrogens. 1, 2, 3, 4, 5, 6, 7. There's a methyl group on carbon 5. This is 1, 2, 3, 4, 5, 6, 7. Methyl group is 1 carbon. And now I'll put in the hydrogens because I know there's 4 bonds to carbon. And that's how you do it. Oh, let's do one more. Let's do a ring. And why don't you try this one? Draw the structure for 1-ethyl cyclopentene. This one might be a little tricky. Let's see if you're up to it. And a commercial from Dr. White. Don't forget, I have my office hours tonight from 5 to 6:15 on Zoom in the syllabus and also on D2L homepage for 170. Come 170, I have the Zoom login for my office hour. If you have any questions, stop by, say hello, and ask your questions. I think 2 semesters ago, I had a student come to my office hour, and I say, "Where are you?" He says, "Oh, I'm sitting in an ambulance." I say, "Are you okay?" He says, "Oh, I work on an ambulance. It's a private ambulance company. We just dropped someone off at the hospital. I've got some downtime. I thought I'd log in with his tablet and talk to you." Quite unusual. But anyways, everybody done? Yep. All right. Let's do it. Start from the right and move left. E-N-E ending, double bond. If that were A-N-E, cyclopentane, pentane 5 carbons, cyclo a ring. Now it doesn't matter where you put the double bond. I'll show you that. Here's my double bond. Now one of the carbons has to be 1, the other 2. So I'll make this 1 and it has an ethyl group on it, 2 carbons. That's one way of drawing it. You could have drawn it also this way. And there are a lot of other variations. All those would be the same way. All I'm doing is rotating the ring around. In this case, I flipped it along this axis 180 degrees to get to this one here. But these are the same. And if you, luckily you have an instructor who knows organic chemistry. Any questions on nomenclature of alkenes? We'll come back to alkenes when we talk about cis and trans fats later in the semester. All right, we're going to come back to triple bonds, nomenclature, and everything a little later because Dr. White wants to get into the good stuff. And let's get into the good stuff right now. And let's talk about reactions to double bonds. Alkenes, double bonds. Alkenes undergo what we call addition reaction. That's where the pi bond, remember a double bond, and you should know this, switches on full. My spelling isn't, or writing. And I'll show you what you need to know. Now, one of the things I should teach you up front is in math, and you are familiar with x plus y equals, say, 100. And x and y we call variables. If x is 10, y would be 90. If x is 50, y would be 50. And they're numbers. Now, in organic chemistry, we use a variable r. R means anything with carbohydrates in it. 1, 10, 100, 1,000,000. And the way I have it here, and there's another way I can show you, an addition reaction, and my software doesn't like to put carbons in. It does every bend in a line. If you have a double bond, you break the pi bond. Remember, double bond is 1 pi bond, this you should know, and 1 sigma bond. I can break pi bonds real quick and have a lot of fun. Sigma bonds are very hard to break. In my class, other than combustion, when you burn something, you don't break a sigma bond. So what happens is you break the pi bond and 1 carbon gets A and 1 carbon gets B. And we call that an addition reaction. So essentially, you're adding something to each carbon of the double bond. And that's an addition reaction. But let's talk about specific addition reactions. And now Dr. White is real happy. And let me remember, and I'll remind you often, in this class, carbons, single bonds, sigma bonds, almost never broken except for combustion. And I don't teach anymore ozonolysis reaction with ozone, O3. Finally, we're getting into the good stuff. Let's talk about hydrogenation. I will never ask on a test or a final the name of a reaction, but I'll use it because I know it. And the first one is called hydrogenation. And that's the addition of hydrogen, H2, to an alkene, double bond. We talk about this as hydrogen gas, which is H2 as opposed to the element. And you need a catalyst like platinum, palladium, or nickel. Now, here's our general reaction. And a better way of writing it, any double bond, you react with hydrogen and a catalyst, where the catalyst equals platinum, palladium, or nickel. You break the pi bond, and each carbon has a hydrogen on it of the double bond. And you don't break carbon-carbon single bonds. Now notice here, I started with 2 bonds or lines, and I end up with only 1. Why? Because you broke the pi bond. Remember, this has 1 pi bond and 1 sigma bond. Pi bonds you can break all day, easily, quickly. Sigma bonds, you don't. Is that professional? Well, it worked. Let's take a look at this. Now, on a test and in real life, organic chemists want to predict products mostly, or rarely, like almost never, balanced chemical equation. Now, let's take a look at the following. It says, give the organic product or products for the following. Let me remind you up here, if you have a chemical reaction, A plus B makes C. These are the reactants. Which, being an industry, I'll call the starting materials. And here, C at the head of the arrow is called the product. So the question is, how do I figure out the products? Now, watch closely. Look for what's different. What's not a carbon-carbon single bond or carbon hydrogen should get your attention immediately. Oh, a double bond. What am I reacting with? Hydrogen, H2. By the way, we can write above and below the line. We're lazy. Instead of putting plus organic chemist, then I have platinum. That's the catalyst. Remember, for this general reaction, the catalyst can be platinum, palladium, or nickel. What happens? You break the pi bond, and each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So this bond to this carbon and this, so you're going to still have all 3 carbons together, bonded together. Now, I broke the pi bond, and my general reaction tells me each carbon double bond gets a hydrogen. That's these 2. And then I know there are 4 bonds to carbon, so I can put in the rest that are hydrogens. Now, listen carefully. On my test, you'll be drawing structures. You can write it like this, or you could, which I recommend you don't. This carbon has 3 hydrogens, 1 plus 1. The second one has 2. And the last one, 1 plus 2, has 3. Now, you can draw it either way, but the bottom one is an extra step. I don't know about you, but when I'm taking a test, I'd like to do the minimal amount of work to get the right answer. And therefore, you can write it either way. I don't know if I told you this, but I'm that close to the person grading the test in this class, me. So you don't have to do the extra step to bring the hydrogen up. Eh. Now, this is what we call the general reaction right here. And if you don't know that, guess what? You can't do this problem. Therefore, remember what I said last week, how to memorize things, write it down 5 times and say it. Double bond, hydrogen, catalyst. Break the pi bond, each carbon gets a hydrogen, and the catalyst is this, platinum, palladium, or nickel. And do that 5 times and do that twice on different days, and you'll know this. Let's do another one. Oh, by the way, organic chemists were running out of room, bend arrows. And let's look at how do you do this one? Well, you look at this and say, what's different in that molecule? What's not a carbon-carbon single bond or carbon-hydrogen atom and double bond? At that point, all I see is a double bond because carbon-carbon single bonds are not going to react with hydrogen and palladium. Hydrogen, palladium is the catalyst. Remember, the catalyst can be platinum, palladium, or nickel. And you break the pi bond, and each carbon of the double bond gets a hydrogen. Notice 2 bonds or 2 lines, 1 line. I broke the pi bond. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. The 2 carbons of the double bond, I broke one of the bonds. Notice there's no longer 2 lines, just 1, the pi bond. Each one, my general reaction tells me, gets a hydrogen. And I know there are 4 bonds to carbon, so I can put in the remaining hydrogens. And that's how you do hydrogenation. I should mention, at 2 companies I worked for, I supervised in chemical plants this reaction, doing it on 40,000 pounds of chemicals at a time. How many of you are familiar with the vehicle that delivers gasoline to gas station? You all seen that? Those are called tank wagons. They're standardized. Tank wagon holds 5,000 gallons, which is equivalent to 40,000 pounds. So I've done this reaction on numerous times at either both company, both in the lab, but in the plant when it gets exciting, on 40,000 pounds. That's $40,000 of somebody's money, plus time and labor, which means more. Oh, I better let you have some fun. And have some fun. What would be the organic product or product for the following reaction? Now we're getting into the good stuff. This is much more exciting than nomenclature. And when you're done, give me a thumbs up. All right, I think everybody's done. Now let's look at this molecule. The question is, give the organic product or product, what's different? Ooh, double bond. Again, look for what's different. You're gonna, by the end of the semester, have nightmares hearing me say, look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atom. That's where the action is, double bond. Reacting with hydrogen, H2, nickel is a catalyst. Catalysts are platinum, palladium, or nickel. In this case, it's nickel. Break the pi bond, because you should know double bonds, one pi bond, one sigma bond. Sigma, we don't break. Pi bonds, we do, and I did. That's why you only see one, not two lines. And that's hydrogenation. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 carbons. I better end up with 4 carbons. Which are my 2 carbons of double bond? These 2. I break the pi bond, each one gets a hydrogen. So these 2 get a hydrogen. And now I know there's 4 bonds to carbon. Remember, it's now your solemn responsibility that if I make a mistake putting in hydrogens, it's your job to tell me so I can correct it. And that's how you do it. Now, one of the questions you should be asking is, what's so important about hydrogenation? How many of you have heard of hydrogenated fats and oils, which are not good for you, but companies use those in products? All they're doing is taking a double bond, like I just showed you, hydrogenating it, making a single bond. I'll talk more about that when we get into fats and oils way down the semester. Now let's look at the following, and I'll do this one. We look at this reaction, what do you have? Oh, I've got a ring, but no, look, what's different? Double bond. And I'm reacting with hydrogen and platinum. So double bond, hydrogen, and a catalyst. And the catalyst can be platinum, palladium, or nickel. And when you break the double bond, each carbon of the double bond gets a hydrogen. Well, in a ring, we don't show hydrogens. So if I break the pi bond, I'm done. Are you really? Is that right? Well, let's take a look. These are my 2 carbons of double bond. How many hydrogens on that carbon? Well, I see 3 bonds. 4 minus 3 is 1. We don't normally show it. Same thing here, 3 bonds. 4 minus 3 is 1. Now let's look at this carbon. How many bonds? 2. 4 minus 2, 2 hydrogens. Same thing up above. So we did add that hydrogen. We just don't show it. Speaking about showing it, I went a whole minute into our break. I'm going to give you a full break. Time to take a break again. Come back at 2:51. And I'll see you in 5 minutes. Oh no, I'm a minute late. Let's get going. Or I can use this one. I love that. Welcome back, everybody. Sorry I'm late. I went and got my mail, and Sign of the Times had the yellow pages, which is about this thick. When I was a kid, the yellow pages before computers and the internet, yeah, there was a time like that in our world. The yellow pages was about this thick. I mean, who uses the yellow pages that you can't get online? Anyways, let's get back to organic chemistry. Now, again, double bond, hydrogen and catalyst, you break the pi bond, each carbon gets a hydrogen. Now, why do you need a catalyst? Well, catalyst makes a reaction go quicker and is not consumed, doesn't become part of a new molecule. And if you didn't have a catalyst, you could put hydrogen and a molecule with a double bond together and come back a month or two later, not much will happen. If you use a catalyst, because I worked in this area, I know it quite well, at 130 degrees Celsius with hydrogen and a catalyst, it's done in about 4 hours. And in industry, time is money. So the quicker you can get something done, as opposed to waiting months, do it in a couple hours, you save a lot of money. Makes sense. And dollars too. All right, let me have you try one. Uh-oh, hold on. I've got to close down something. All right, we're back in business now. I don't know why at times it hangs up on, I know why. I've got a tablet, a webcam, and a whole lot of other things going on, including attached to Zoom or connect to Zoom. All right. And let's do the following. Give the organic product or products for a following reaction. 3 points each. All right, is everybody done? Let's get going. And the question is, what's the organic product or products following the reaction? And I did something that's the chemistry instructor's trick on a test on you. Shh, don't tell anybody I'm giving away secrets, but right here, I have a big scary molecule. If you don't know what it is, it's a big scary molecule. And you go, eek. Hopefully you don't have to go eek. And what do? No, you look for what's different. What's not a carbon-carbon single bond or carbon hydrogen should get your attention. Double bond. What am I reacting with? Hydrogen and nickel is a catalyst. And it could be nickel, platinum, or palladium. And you break the pi bond. Remember, double bond, one pi bond, one sigma bond. You don't break sigma bonds, and each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So immediately I can draw this, have my T-butyl group still there because it comes along for the ride. Let me redraw this so it looks nicer. That's better. Anyways, hold on. Dr. White's having a bad ring drawing day. Let me try it again. Notice I broke the pi bond and I'm done because you don't show hydrogens on a ring. And that's how you do it. Oh, let's do one more for fun. Anybody have a question on the one I just did? Again, you don't break carbon-carbon single bonds, 6 carbons in a ring. I'm not. The T-butyl is still going to be there. Double bond goes to single bond. And the ring, you just, instead of 2 lines, show 1 line. And that's how you do it. Anybody have questions? I see a question on somebody's face, sort of. Did that help out when I explained it? All right, let's do one more. And there's one for you to try. I don't know what letter it is. Let's call it E for whatever. Give the organic product or products to the following. Thank you. I see one thumbs up. A couple. Oh, everybody's done. Doesn't it feel good? You're learning organic chemistry and it's doable. All right, let's do this. How do we do this? We look at this molecule and say, what's different? What's not a carbon-carbon single bond? What's not a carbon-hydrogen atom? Ooh, a double bond. I'm reacting it with hydrogen and a catalyst. And the catalyst can be platinum, palladium, or nickel. And you break the pi bond, and each carbon of the double bond gets a hydrogen. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, plus 2 methyls. 1, 2, 3, 4, 5 across, plus my 2 methyls. I like to put hydrogens in at the end. Notice I broke the pi bond, and each carbon of the double bond that was originally the double bond, these two get a hydrogen as per our general reaction. And now I know there's 4 bonds to carbon. And I can put in the rest of the hydrogens. And that's how you do hydrogenation. Now, unfortunately, in this class, I don't talk about reaction conditions. And the other thing is, I don't talk that much about what I call cost accounting. In fact, most of the chemists at ECC or at the other school I teach don't know that, because a lot of them have never worked in industry like I have for a number of decades. I shouldn't have said that. Yep, decades. But anyways, if you're in industry, you use nickel. It's cheap, inexpensive. If you're into pharmaceutical or use research and an academic, use platinum or palladium, because it gives a cleaner reaction at that small scale. But when you're talking about money and cost, you use nickel, unless you're making medicine, which you can charge a lot more for. But I won't ever ask that on a test, but that's real life. All right, does everybody see on the screen Dr. White's favorite online periodic table? One of these days, I've got to look up who created this, send them an email thanking them for doing a wonderful job. This is the periodic table. Now, I like to remind you about something, and that is fluorine, chlorine, bromine, and iodine. I've never worked with astatine, and you won't, but I have with fluorine, chlorine, bromine, and iodine. Those are called the halogens. If you see up to here, we have the halogens, and they show you which ones they are, but it's fluorine, chlorine, bromine, and iodine. And why am I telling you this? Because we're going to work next reaction with halogenation of double bonds. And that involves either fluorine gas, chlorine gas, bromine gas, or iodine. And let's take a look at that. Now, somewhere, someone decided for the halogens, everybody see halogenation on your screen? Thank you. X equals fluorine, chlorine, bromine, or iodine, the halogens. And halogens exist as a gas as X2, diatomic, just like hydrogen exists as H2, oxygen exists as O2. And here we have a double bond reacting with halogen gas, where halogen can be fluorine, chlorine, bromine, or iodine. You break the pi bond. Let me write it this way. And each carbon of the double bond, just like hydrogenation, instead of hydrogen, gets a halogen, X. Now, it turns out because of the bond energies involved, you don't need a catalyst for this reaction. It goes quite quickly. And not this week, but next week when we do our lab, our first lab, no, actually it's 2 weeks from this Wednesday, because next, a week from this Wednesday, we'll do melting points. You'll see this and it goes real quick. I have a YouTube video of it. So this is halogenation. Now, one thing I neglected to mention, I've mentioned it before, but I should have. If you look at a general reaction, notice how I've always been writing the general reaction underneath. Some of my best students I've ever had in organic chemistry, on their test, every question like this, you see the general reaction written underneath. Some of the best students I've ever had in Chem 170 organic chemistry, they never write the general reactions underneath. I always will, because it helps you learn it better. But you can go either way. But if you don't know this, it's like not having a roadmap or GPS. You're trying to go from Elgin to, say, where would be a good place? Oh, Salt Lake City, Utah. If you didn't know, have a map or a GPS, you're not going to get there that easily. Eventually you will, but you're not. If you couldn't stop and ask for directions, you probably wouldn't get there. So let's look at halogenation. And the question would be, give the organic product or products for the following. Now, why are these reactions important? Because these are the building blocks we use to make things that you use in your daily life, like your soap, your fabric softener, medicine you take, things you use to clean your house, things you use to gargle with in your mouthwash. They're all made by organic reactions, and a lot of them I'll be teaching you this. So if I look at this reaction, how do you do it? You look for what's different. Ooh, double bond. I'm reacting it with bromine gas. That's the halogen. Remember, X can be fluorine, chlorine, bromine, or iodine. And you break the pi bond. Remember, each carbon of the double bond, there's a pi bond and a sigma bond, and each carbon gets a halogen of the double bond carbons that are no longer double bond carbons. Do you break carbon-carbon single bonds? No. So I have 4 across. I'm going to have 4 there. Now, this is important. Which carbons have the double bond carbons? Those are these 2. And those are the 2 that will get the halogen. What's X? Bromine. And that counts the same as a hydrogen 1 bond. And notice I put the hydrogens in. Now, why would you want to put a halogen on there? Well, you can do other reactions with the new molecule. And a while back, they found that the more halogens you put in a molecule, the more flame retardant you make that. The more halogens you put, now replacing hydrogens with halogens make molecules flame retardant, and some of those are used in things like making flame retardant clothing for our children, which is a good thing. Because if a child gets, in the old days, near a candle or a room heater, in the winter time, people have those in their homes or apartments. Their pajamas could catch on fire. With a flame retardant, it's going to be less likely they're going to get burned that way. And here's one for you. Give the organic product or products for the following reaction. 3 points each. We're doing some serious organic chemistry. And when you're done, don't forget, thumbs up. All right, let's do it. Look at a molecule, look for what's different. What's not a carbon-carbon single bond, carbon hydrogen should get your attention. Ooh, double bond. And as soon as I see that and look at the rest of the molecule, carbon-carbon single bonds, carbon hydrogens, all I think about is the double bond. Reacting with fluorine gas, and that's a halogen. Remember, X can be fluorine, which it is, chlorine, bromine, or iodine. You break the pi bond. Remember, this is one pi bond, one sigma bond. Pi bonds you break, sigma bonds you don't. And each carbon of the double bond gets the halogen. I have 1, 2, 3, 4, 5, 6. I better end up with 6 across because you don't break carbon-carbon single bonds. Now, it's important which carbons the halogens go on, because if you don't get them right, I mark it wrong in real life, it could cause serious problems if you get the wrong product. And these are the 2 carbons, the double bond. I broke the pi bond. Each one gets a fluorine. I know there's 4 bonds to carbon, so I can put in my hydrogens. Any questions so far? All right, well, in that case, let's do one more. These are fun. I'm having a good time. I hope you are. And here's one more for you to have fun with. Give the organic products for the following. All right, I think everybody's done. Let's do this. Now, we look at this reaction and say, what's different? What's not a carbon-carbon single bond or carbon or hydrogen? Oh, look, there's a double bond. And that's all I see now in that molecule, because that's where all the action is. And I'm reacting with chlorine gas, and chlorine is a halogen, and we abbreviate that in organic chemistry by X. It can be fluorine, chlorine, bromine, or iodine. And what happens? Remember this one pi bond, one sigma. You break the pi bond, and each carbon of the double bond gets a halogen. Now, do you break carbon-carbon single bonds? No. So I'm still going to have my ring. These two methyl groups, CH3, are going to come along for the ride. They don't disappear. Notice I had two lines here, one here, and my general reaction says each one of the carbons of the double bond gets a halogen, in this case, chlorine. And that's the molecule. Now, you don't have to draw in the C's like I did, but here's your answer. And that's how you do halogenation. Do I have time? I do. About 3 or 4, maybe even 5 years ago, these 4 reporters from the Chicago Tribune did a tremendous service to us all. And what they did was, for many years, especially this one company that made it, they made fire retardants, not only for clothing, but for things like the plastic of my monitor, right up around, I'm looking at right now, for things like the fabric of your couch and other things in your home. And everybody said, oh, fire retardant, you need to put this in there. It helps keep things from burning. You can never stop anything from burning, making it fireproof. If it can burn, eventually it will, but you can retard it. Well, these reporters went back and traced, where did this come from? Because a lot of the chemicals that are used for fire retardants are halogens. Unfortunately, smaller molecular weight halogens are carcinogens. Not good. That means they cause cancer. Well, they went back and found there was this company, and all the claims for putting fire retardants in plastic, the types this company made, came from this one Swedish article that sort of said, well, maybe this might be good or not, but there wasn't concrete proof. Well, nobody ever went back and checked that article. And turns out a lot of these, in certain applications, those fire retardants didn't do any good and actually did harm. How? Well, it got into the air, like if it was on your couch and you're breathing it in, you could get cancer. And they did a good service. Oh, one other thing. Throughout the semester, I'll give you some what I call public service stuff that my knowledge of organic chemistry helps me. Back in the 40s and 50s, and then through the 60s maybe, dry cleaners used 2 chemicals, mainly carbon tetrachloride, carbon with 4 chlorines on it, as the liquid they did the dry cleaning in. Dry cleaning is they wash your clothes or whatever in something that doesn't have water. Well, carbon tetrachloride is extremely carcinogenic. It causes cancer really bad. But some of these unscrupulous dry cleaners, after they clean your clothing or enough of it, the liquid carbon tetrachloride was dirty, like dirty water in a bathtub or whatever. You couldn't dump it down the drain, and they didn't want to pay money to have it disposed of. What did they do? Well, they went across the street if there was an empty field, and they dumped it, and it got absorbed into the ground. Guess what? Those areas now have high carbon tetrachloride levels and are carcinogenic. What does this mean? If you're going to buy a new house, make sure you check that where you are going to buy your house, nearby block, or I don't know how nearby, but nearby. There was never a dry cleaner, and there's ways of doing that online. Because I don't know about you, but I sure don't want to live near a place where you could get cancer. And turns out a number of those sites in Chicago have been tagged, and they're still on the list. I think the Superfund, EPA Superfund, to one of these days get cleaned up if they haven't been already. All right, if you notice the double bond chemistry I've shown you, double bond plus hydrogen and a catalyst, each carbon gets a hydrogen, double bond plus halogen, remember X is fluorine, chlorine, each carbon gets a halogen. That's called symmetrical addition, which I'll never ask on a test because both carbons of the double bond get the same atom, hydrogen or halogen. What happens if it's different? And one could get one atom and the other carbon double bond could get something else. And we call those unsymmetrical addition reactions. And turned out this caused a major dilemma for organic chemists. Which carbon gets one and which gets the other of the two things you're adding? Well, a great Russian organic chemist, Markovnikov, investigated this, and I honor his great work, and organic chemists do this by using his name, and he came up with a rule, and it's called Markovnikov's rule. Do not write this down, because I have an easier way for you to memorize it. And Markovnikov's rule is when an unsymmetrical molecule will form HA or HQ adds to an unsymmetrical alkene double bond, the hydrogen from HA or HQ becomes bonded to the unsaturated carbon atom that already has the most hydrogens. What? Well, let's look at this and make it easier to understand. But Markovnikov, this is a lifetime achievement to understand this and solve this problem. So let's look at an example, addition of an acid to alkene. And I'll write it again, double bond, HX, HX is an acid. Now in this case, X will just be chlorine, bromine, or iodine, not fluorine, because HF, hydrofluoric acid, is one of the most dangerous chemicals around. You get it on your skin, it will eat all the way to your bone. In fact, of all my years doing chemistry, there's only one time all my career I refused to work on a research project that was given to me. And that was dealing with HF, hydrofluoric acid. I told the vice president of the research and development, I'm not going to do this. Do you want me to leave the company? He said, no. They found someone else. That person actually had a nervous breakdown from the stress working with HF. Now, what happens is you break the pi bond. One carbon gets the H from HX, the other gets X, and it follows Markovnikov's rule, which I used to write it out, but I'd spell it wrong half the time. So to save time, I just put down M's rule. That's the general reaction. Let's look at how you do this, because it's something you got to work at, but it's doable. Again, let's look at the following. What do you see that's different? Secretly, I'm brainwashing you to look for that because I do instinctively and I see a double bond and nothing else will get my attention. The rest is carbon-carbon single bonds and carbon-hydrogen. I'm reacting with HCl. Remember, halogens are X, And for this reaction, X is either chlorine, bromine, or iodine. I'll never on a test put HF because that's not right. I don't do that. That violates my golden rule of teaching, which is don't do unto your students what you didn't like done to you. And you break the pi bond, one carbon gets the H, and the other carbon gets the X. Now, how do you know which? Markovnikov's rule. Now, better way of remembering Markovnikov's rule. The hydrogen from HX goes to the carbon of the double bond with the most hydrogens. The hydrogen from HX goes to the carbon atom of the double bond with the most hydrogens. Well, it's time to use your high-level math skills. It's going to get tough now. Which is greater? This carbon has two hydrogens. This one has one. And the answer is 2. So the hydrogens will go to this carbon, and the halogen will go to this carbon. Do you break carbon-carbon single bonds? No. So I still have 3 carbons. I break the pi bond, and my hydrogen will go to the carbon with the most hydrogens, and the halogen, in this case chlorine, will go to the other one. And a halogen counts as one bond, so I can put in that. And that's how you do Markovnikov's rule. Now, when I was in undergrad taking first semester organic, my instructor had another way of helping us remember it. I hate to say this, should I? Yeah, this is decades ago. Decades ago, I still remember it. And one way he taught us is, remember Markovnikov's rule, the rich get richer and the poor get poorer. We're talking about hydrogens. And the other way he taught us, and I still remember it, is, and it's not good English, them that has it gets it. And we're talking about the hydrogens. Well, let's go through it again. Double bond. You break the double bond, one carbon gets hydrogen, the other gets the halogen. And how do you know which? You say the carbon of the double bond with the most hydrogens gets the hydrogen, and the other carbon gets the halogen. Therefore, this has 2 hydrogens. You got the hydrogen. The one with only one hydrogen gets the halogen chlorine. And that's Markovnikov's rule. Now, listen carefully. If you draw this structure right here, I'm going to mark it wrong and give you 0 points because it's wrong. And you might say, well, I got it sorted right. No, you didn't show me you understood Markovnikov's rule. In this class, where you put atoms are very important. Placement is important. How many of you have taken anatomy and physiology? A number of you. And if you, I've never taken it, but if they ask you to draw a hand and you put the thumb over here next to the pinky, do people still call the end finger the pinky? Anyways, put it over here. It's wrong. And it's just that, like night and day. Is it dark or light out when the sun's up? If you put down dark, no, it's light out. Even if it's cloudy, it's still lighter out than middle of the night. Atom placement is critical in organic chemistry. And why don't you try this one for your fun and enjoyment on this Monday afternoon? And when I'm done teaching here, I get to put my garbage out because Monday night is garbage night. Exciting. All right, see, some of you are done, some are still working. Oh, I think everybody's just finished. All right, let's go through this. How do you know what's the product? Because the question is give, and that means draw. And you see something like this on a test and say this were A. And what do? Well, you look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen? Ooh, a double bond. That's the only thing that's different. Reacting with HBr. And halogen, bromine, HX. Remember, for this reaction, X is chlorine, bromine, or iodine. You break the pi bond, one carbon gets H and the other gets the X. And how do you know? It follows Markovnikov's rule. The carbon with the most hydrogens, the double bond, gets the hydrogen from HX and the other carbon gets X. So if we look at that, two carbons, a double bond, look out, I'm going Technicolor on you. Anybody still have black and white monitors? I never ask anymore. Anyways, this has two hydrogens. This has 0. Which is the higher number? Isn't the math hard in organic chemistry? Hopefully all pick 2. Now, do you break carbon-carbon single bonds? No, so I have 4 across plus a methyl. Here are my 2 carbons of a double bond. Remember, there's a pi bond, which I break, and a sigma bond, single bond, I don't. And the carbon with the most hydrogens, the N carbon will get the hydrogen, and the other carbon will get the halogen bromate. And I know there are 4 bonds to carbon, so I can put it. Now you could write this one as CH3. You don't have to. Why do an extra step? You're under enough stress as it is. And that's how you do Markovnikov's rule. Again, you look at the double bond carbons and count the number of hydrogens on that carbon. The carbon with the most hydrogens gets the hydrogen from HX. The other carbon gets the halogen. And we use this reaction to make things like a molecule like this that I can further react to make things we use in our daily life, including perfume, medicine, and other things. And that's Markovnikov's rule. We'll do some more, but there's a few things I'd talk about before we end up today, which we're just about out of time. Boy, time flies when we're having fun with double bonds. But anyways, remember, do the practice problems. You're not going to learn organic chemistry a night or 2 before a test. You're not. It's not going to be pretty. You're not going to enjoy the results from that. Keep up. On Wednesday, I'll go through chapter 2. There wasn't one for chapter 1, problem set. On Wednesday, the beginning of the class, I will teach you my method, how to eliminate test anxiety, but I'll cut it out of it. I like that special effects. I'll cut it out of the video, so I don't want that floating around the internet. Someday I might try and sell it. And that will be helpful. And we'll continue on. Now, just to remember, it's getting dangerous out there, as it already has been. Wear a mask. And if you haven't, get your vaccine. I don't know if I've told you this, but all throughout my life, certain shots I have really reacted badly to. About 10 years ago, I got a tetanus shot because I got cut by a rusty nail and I needed a tetanus shot. And for 2 days, my left arm was paralyzed. I couldn't use it. It was just worthless. That wasn't fun. When I got the Pfizer last April, both injections, nothing happened. I was shocked because I was ready for the worst, but I knew it was necessary. And all I had was a little discomfort that evening in my arm, which they warn you about. And they say, you know, go like this, work the muscles. The next morning it was gone. So get vaccinated if you haven't. It's free. It's available everywhere. And I'm going to do something unusual. I'm going to let you out a whole minute early. Shh, don't tell anybody I'm doing that. With that, I'm going to say, gain gesund, be healthy. I'll see you Wednesday morning. And don't forget, I have my office hour tonight, 5 to 6:15. Bye now.